You open your phone without thinking about it. You type a question into an AI tool, maybe something simple like, "What should I eat today?" or something bigger like, "Write me a full script." And within seconds, an answer appears. Clean, structured, almost like it came from a person sitting right next to you. It feels light, effortless, almost invisible. No noise, no heat, no sense of weight. Just words appearing on a glowing screen. And because it feels so easy, it's natural to assume that it doesn't cost much. That somewhere out there, this system is just quietly working in the background, like a calculator. But what you don't see is that every single one of those answers travels through a physical world that is anything but light. A world filled with massive buildings, miles of cables, machines that burn through electricity, and entire systems designed just to keep that one response flowing to you in under a second. Imagine this instead. Somewhere far away from you, there is a warehouse-sized building with no windows, sitting in the middle of an empty landscape. Inside, row after row of metal racks stretch out in every direction, each one filled with powerful computer chips. The air is loud, constant, like a never-ending hum of fans pushing heat away as fast as possible. The temperature is controlled carefully because if it rises even a little too much, everything inside could start to fail. Lights flicker softly, cables run like veins across the floor and ceiling, and all of it is working at the same time. Not for one person, not for one request, but for millions of people doing exactly what you just did, asking a question and expecting an answer instantly. And here's the part that changes how you see it. That one simple request you made, something that felt like nothing, triggered activity across this entire system. Chips turned on, calculations started flowing, energy moved through circuits, and heat began to build up immediately. Because AI isn't just thinking, it's calculating. And those calculations are happening at a scale that's hard to picture unless you slow it down and really see it. Think about a single moment. You type a sentence. You hit enter. Now imagine that instead of one brain answering you, there are thousands of tiny operations happening at the same time. Numbers moving, patterns being compared, probabilities being calculated over and over again until the system decides what word comes next, then the next, then the next. It's not magic, it's repetition at extreme speed. And repetition, when multiplied enough times, starts to consume something very real, electricity. Now zoom out for a second. You're not the only one doing this. Millions of people are asking questions, generating images, writing code, editing videos, all powered by similar systems. Every one of those actions adds up. It's like turning on a light. One light doesn't matter much, but imagine a billion lights turning on at the same time. That's closer to what's happening. And this is where things start to feel different, because the more useful AI becomes, the more people use it. And the more people use it, the more energy it needs. It's not a small increase, it's exponential. The kind of growth where something that feels manageable today quietly becomes massive tomorrow. If you could stand inside one of these data centers, you wouldn't see intelligence. You wouldn't see thoughts or ideas. You would see machines working as hard as possible, pushing electricity through circuits, converting energy into heat, and then fighting that heat just to keep going. You would feel the air moving constantly, like standing behind a giant fan that never turns off. And you would realize that every answer you get, every sentence, every idea, has a physical cost. And the strange part is that this cost is mostly invisible to us. When you charge your phone, you see the cable. When you turn on a stove, you feel the heat. But when you use AI, there's no obvious signal that something heavy is happening in the background. It feels weightless, but it isn't. The reality is that AI systems are powered by some of the most energy-hungry machines ever built. These machines are designed to process massive amounts of data as fast as possible. They don't rest, they don't slow down, and they don't just turn on when you use them. They are running constantly, ready to respond at any moment, which means they are constantly consuming electricity, whether you're thinking about them or not. And this raises a bigger question. If something that feels this small is actually this heavy behind the scenes, what happens when it becomes part of everything? Because that's the direction things are moving. AI is not staying in one app. It's spreading into search, into work tools, into education, into healthcare, into almost every system we interact with. And every time it spreads, it brings its energy cost with it. quietly, invisibly, but very real. You can start to picture it like this. Imagine the internet in its early days. A few websites, simple pages, limited use. Now compare that to today, where everything is connected, always on, always updating. AI is at the beginning of a similar curve. And if history repeats itself, the demand for energy is going to rise faster than most people expect. And here's where things become even more interesting. Because the challenge isn't just about having enough electricity, it's about delivering that electricity exactly where it's needed, at the exact moment it's needed, without interruption. These systems can't just pause. They can't say, try again later. They are expected to respond instantly, every time, which means the infrastructure behind them has to be incredibly stable, incredibly fast, and incredibly powerful. Now imagine scaling that up, not just for one company, not just for one country, but globally. Millions of servers, billions of requests every second. At that point, AI stops being just a software story. It becomes an energy story. And once you see it that way, everything changes. Now imagine zooming in even closer, past the massive buildings, past the rows of machines, down to the tiny pieces that actually do the work. At the center of all of this are small, flat chips that don't look like much at first glance. Thin squares, almost simple. But inside them is where everything happens. Millions, sometimes billions, of tiny switches turning on and off at incredible speed. Each switch represents a tiny decision, a yes or no, a 1 or a 0. And when you stack enough of those decisions together, you get something that feels like intelligence. But here's the catch. Every one of those tiny switches needs energy. Not a lot on its own, almost nothing. But when you multiply that by billions, and then multiply that again by how fast they're switching, and then multiply that again by how many chips are working at the same time, suddenly you're not dealing with something small anymore. You're dealing with something that consumes an enormous amount of power just to keep those switches moving. You can think of it like a stadium full of people all flipping a light switch at the exact same time, over and over again, as fast as they can. One person flipping a switch is nothing. A stadium doing it non-stop is something else entirely. That's closer to what these chips are doing every second. And there's another layer to this that most people never see. When electricity flows through these chips, it doesn't just disappear after doing its job. A lot of it turns into heat, real physical heat, the kind that builds up quickly and starts to become dangerous if it's not controlled. So now you have a second problem. Not only do you need to power these machines, but you also need to cool them down constantly. That's why inside those data centers, the sound never stops. The fans are always running. Air is always moving. In some places, they even use water systems, pushing liquid through pipes to absorb heat and carry it away. Imagine trying to keep thousands of laptops running at full power inside a closed room without letting them overheat. That's the challenge, just at a much larger scale. And the more powerful the chips become, the more heat they produce, which means the cooling systems have to work even harder, which means even more electricity is used, not just for thinking, but for surviving. So now you have this cycle. More demand for AI leads to more powerful chips. More powerful chips use more energy. More energy creates more heat. More heat requires more cooling, and more cooling uses even more energy. It's not a straight line, it's a loop that keeps growing. And this is where things start to push against real limits. Because electricity isn't infinite, it has to be generated somewhere. It has to travel through wires across long distances, through systems that were not originally designed for this kind of demand. And when you suddenly increase how much energy is needed in one place, you start to feel it. You can picture it like a city that was built for a certain number of cars. The roads work fine at first, traffic flows, everything feels smooth, but then more and more cars start showing up. At some point, the system can't keep up. You get congestion, delays, bottlenecks. The system wasn't designed for that level of pressure. That's what's starting to happen with energy and AI. In some parts of the world, data centers are already using as much electricity as small cities. Not in theory, in reality, entire facilities drawing huge amounts of power every second just to keep up with demand. And as AI grows, those numbers are expected to rise even more. And it's not just about how much energy is used, it's about when it's used. AI systems don't follow a simple schedule. They don't only run during the day or slow down at night. People are online all the time across different time zones, constantly interacting with these systems, which means the demand for energy stays high around the clock. That creates a different kind of pressure. Energy systems are usually built with patterns in mind. Peaks during the day, lower use at night. But AI starts to flatten those patterns, keeping demand consistently high, and that's harder to manage. Now step back again and look at the bigger picture. You have a technology that is becoming more useful every day. More people rely on it, more companies build around it, and every improvement, every upgrade, every new feature tends to increase how much computation is needed, which increases how much energy is needed. So the question slowly shifts. It's no longer just, how powerful can we make AI? It becomes, how much energy can we afford to give it? And that question doesn't have an easy answer, because on one side, the benefits are obvious. Faster tools, better systems, more automation, new possibilities that didn't exist before. But on the other side, there is a physical cost that keeps growing quietly in the background. And unlike software, you can't just scale energy infinitely without consequences. You have to build power plants. You have to expand grids. You have to manage resources. All of that takes time, money, and planning. So now you have two worlds moving at different speeds. Technology moving incredibly fast, improving almost every month. And infrastructure moving much slower, trying to keep up. And in between those two speeds, tension starts to build. Now here's where things take a turn that most people don't expect. You might think the solution is simple. Just make the systems more efficient. Make better chips, smarter code, cleaner energy, and the problem solves itself. And to some extent, that is happening. Chips are improving. Engineers are constantly finding ways to squeeze more performance out of less energy. Data centers are becoming more optimized. Cooling systems are getting smarter. On paper, everything is moving in the right direction. But there's a pattern that shows up again and again in technology, and once you see it, you can't unsee it. Every time something becomes more efficient, people don't just use the same amount with less energy. They use it more. Imagine your internet suddenly becomes twice as fast. You don't just load the same simple pages faster. You start watching higher quality videos. You open more tabs. You stream more content. The efficiency doesn't reduce usage, it expands it. The same thing is happening with AI. As systems become more efficient, cheaper, and easier to use, more people start using them. And not just casually. They start relying on them for bigger tasks, longer tasks, more frequent tasks. What used to be a quick question becomes a full workflow. What used to take seconds now runs continuously in the background. So even though each individual operation might use less energy than before, the total demand keeps growing. You can picture it like a highway that gets expanded to reduce traffic. For a short time, things feel smoother, but then more drivers start using it. New routes open up. More people decide to travel. And before long, the traffic is back, sometimes even worse than before. This is what's happening with AI and electricity. Efficiency is improving, but demand is growing even faster. And there's another layer to this that makes it even more intense. The size of AI systems themselves is increasing. The models are getting bigger, more complex, trained on more data, designed to handle more tasks at once. And bigger models require more computation, not just when they are being trained, but also when they are being used. Training one of these systems can take an enormous amount of energy. Days, sometimes weeks, of continuous computation across thousands of machines. It's like running a marathon, but instead of one runner, you have thousands running at the same time, all drawing energy from the same source. And once the model is trained, the energy use doesn't stop. Every time someone interacts with it, the system has to perform calculations again. Not as intense as training, but constant, continuous, endless. Now multiply that by millions of users. This is why the conversation around AI is slowly shifting from just capability to sustainability, not in a vague, abstract way, but in a very practical sense. Can the systems that power AI keep up with the demand that AI itself is creating? And the answer is not obvious, because energy systems are not as flexible as software. You can't just double capacity overnight. You can't instantly build new power sources or expand infrastructure at the same pace that technology evolves. There are limits, delays, physical constraints that don't disappear just because demand increases. So what starts to happen is a kind of balancing act. Companies begin to think not just about how powerful their systems can be, but how much they can run them, where to place data centers, how to access cheaper or more reliable energy, how to reduce costs without slowing performance too much. Every decision becomes a trade-off between speed, cost, and energy. And this is where things start to connect to the real world in a way that's hard to ignore. Because energy is not just a technical detail, it's tied to geography, to resources, to infrastructure, to policy. Some places have abundant energy, others don't. Some regions can support large data centers easily. Others struggle to keep up even with current demand. So suddenly, the growth of AI isn't just about better algorithms, it's about where energy is available, where it's cheap, where it's stable, and that starts to shape how and where AI expands. And once you start to see it that way, it becomes hard to go back to seeing AI as something abstract, because it's not just software sitting somewhere in the cloud. It's a physical system, a demanding one, always running, always consuming, always balancing between what it can do and what it can sustain. And the strange part is that the better it gets, the more invisible it feels. You won't see the buildings. You won't hear the machines. You won't feel the heat. You'll just see the result, a faster answer, a smoother experience, a world that feels easier to move through. But behind that ease, something real is being spent every second: energy. And as AI becomes part of more and more of what we do, that invisible cost starts to matter in a way that's hard to ignore. Not because it will suddenly stop working, but because it will quietly shape how far it can go, how fast it can grow, and what it's worth using for. Because in the end, AI isn't just limited by how smart it can become. It's limited by how much of the real world it can use to exist. And that's what makes this moment interesting. We're not just building intelligence. We're building something that has to live inside the same physical limits as everything else. And for the first time, those limits are starting to show. I post videos that break down how reality actually works, from your brain to your body to the world around you. So if that sounds interesting, subscribe, and I'll see you in the next one.